Today we will be going over modeling with nonlinear regression. In this lesson, we will use the exponential regression features on a graphing calculator rather than algebraic techniques to model data exhibiting exponential or logarithmic growth or decay. Let's go over the first example. The internet experienced rapid growth in the 1990s. The table shows the number of users in millions for each year during the decade. Use exponential regression to model the data. Then use your model to predict the number of users in 2008. Let x be the number of years after 1990. This is the stuff we've gone over how to do this in the semester before this. And as you can see, the first step, you make a scatter plot on your calculator by clicking stat and then entering the information in the table. After that, you will find the exponential function to model the data. We do this by using the exponential regression from the list of regression models. Notice that the r squared is close to 1, indicating a close fit to the data. Next, in the y equals menu, pick up this regression equation by entering vars, statistics, EQ, reg EQ. The next step is to graph all the data. The line should be close to the points as you can see here. Now in step 4, the last step, we'll use the model to make a prediction. You do this by, on the calculator, using calc value and then entering 18 for the year 2008, and your y value will be 5,985.666, and of course that's in million internet users, and that's your final answer.
Alright. Another part of this lesson is logarithmic regression. In example 2 talks about logarithmic regression to model data in a table. So problem 2 is about life expectancy. The table shows average U.S. life expectancies according to a birth year. Use logarithmic regression to model the data. Then use the function to predict the life expectancy of a person born in 2020. Let x be the number of years after 1900. So on the board right now are the first 4 years of the table. So insert your data into the table on your calculator. And then it's the same thing that Stephen just went over, except with a logarithmic regression instead. So go to calc ln reg to find the equation. After having made a stat plot on the graph, and the equation should line up fairly well with the stat plot because it is close to 1. And then you go to y equals, and you're going to want to press vars, statistics, EQ, and reg EQ to get the equation in the y equals menu. And then click graph and go to the graph. Afterwards, it's just the exact same thing that Stephen went over, with hitting calc value to find and plug in 120 because it's years since 1900. So the answer is going to be 79.2 years, which is the life expectancy of someone born in 2020. I'm worthless.
Prester John.
Another part of this lesson is logistic growth. Exponential and logarithmic growth is unrestricted, increasing at an ever-increasing rate with no upper bound. In many growth situations, however, the amount of growth is limited by factors that sustain the population, such as space, food, and water. Such factors cause growth that was initially exponential to slow down and level out, approaching a horizontal asymptote. A logistic growth function models such resource-limited exponential growth. Key concept. A logistic growth function has the form f of t equals c over 1 plus a e to the negative b times t power, where t is any real number, a, b, and c are positive constants, and c is the limit to growth. Logistic growth functions are bounded by two horizontal asymptotes, y equals 0 and y equals c. The limit to growth, c, is also called the carrying capacity of the function. For the example question for this logistic growth, we will work with example 3, fish. Use logistic regression to model the data in the table about a lake's fish population. Then, use your model to predict the limit to the growth of the fish population. First, I put in the first 4 numbers in the table, and I made a stat plot. Then, I tried to find a logistic regression to model the data. So you want to go to Stat, Calc, and find the regressions in the same way, but go all the way down past the ones that we've normally been using, and go to Logistic. That's going to give you an equation with this model, where c is just under the limit of the function. So then this is after you've stored the equation in y1, which is done by, before finding the equation, go to store reg eq vars y1, and then find the equation. You can then go to the graph to show the equation, and which can also be used to predict the limit, which, as I said, is just above c and is about 8,498 fish. 99 fish. 99 fish.
Prester John appears again as
Prester
number
John.
9.
Good.
In example 4, we will be choosing a regression from the entire list to find the r squared that's closest to 1 that best fits the data. Use the data in the table to determine a regression equation that best relates the cumulative number of domain names that were purchased from an internet provider each month. Then predict how many domain names will be purchased during the 18th month. On the board, I plotted the first 4. You're going to be doing this in your calculator. First step is make a scatter plot. Second step, you choose a regression to model the data. So you go down the list and you find the one that has the r squared that's closest to 1. You're going to store this by in the calculator, like the last problem using y1. For this problem, the regression would be a quartic equation. Third step, you actually graph it onto your calculator after it is in the y1 menu. You use this data to predict the number of domain names for the 18th month using calc value on the calculator. And the number of domain names after purchased during the 18th month ends up being 564.
Prester John will live on forever.